Okay, ladies and gentlemen, I'm just a stand-in chairman for now because there's a good reason. Our former chair is now being the next speaker, so I have the honor to introduce him. Well, you know him already. It's Steffen Bornemann. He is a polymer scientist and he is working for Folienwerke Wolfen, and he is giving us a talk which is entitled Advantages of cross-linkable interlayer films for application in laminated safety glasses. So Stefan, the floor is completely yours.
Okay, thank you very much. Hello everybody. Now it's my job to, I'm standing between you and the coffee break. Therefore, I would like to speed up a little bit. We will talk about cross-linkable films now as a kind of interlayer. Of course, we heard about PVB, we heard about stiff PVB and also Trossifold. Well, let's talk about cross-linkable films. And as you can see here, okay, wait a second. Can we start again? Go back to first. Thank you. We can see a white screen. That's also good sometimes, but now it's changing from white to black. Yes, okay, thank you very much again. Cross-linkable interlayer films instead of thermoplastic films. This will be our talk for the next few minutes. It's a cooperation with colleagues of mine, Abdus Salam and Yasmin Weiss, who are not here today. I would like to thank them in the beginning already. Let's go through. At first, I would like to talk a few words about Folienwerke Wolfen. We are a mid-sized company in Germany. You will see some numbers about us on this slide. We are located in a city 1 hour south of Berlin. And we have different products, as you can see in a second. Part of it is, of course, the interlayer film. Also, as a small-sized company, we have a strong focus on sustainability, as you heard already this morning several times. We are EcoVadis Bronze certified for a long time already. As you can see here, we have other certifications. We can also work with bio-based materials, in-house recycling, and we use renewable energy, as we heard already. So this is the way that we all should go in industry. Let's see what we are doing beside interlayers. We are a producer of special films. As you can see here, I'm quite sure that all of you have our products in hand, although you never know us. You can see packaging films for medical applications, for tablets, or even we make the films for your credit card or passport. If we want to make good laminated safety glass, then we have to focus on 3 parameters. You can see here, of course, the glass type, the lamination process, and of course, the right interlayer. And if you want to make a good laminated safety glass, then for sure you have to find the right combination out of it to match your or your customers' targets. I want to focus on the interlayer films today. Therefore, I will give you a short introduction into the different types of these films. We heard about interlayer films that are thermoplastic already. As you can see here, PVB or ionomeric are polymeric films that we call thermoplastic. Means they are characterized by the so-called glass transition temperature and the melting point. Compared to this, if we go to cross-linkable interlayer films, they behave slightly differently. If you get them, okay, the material looks the same as a thermoplastic film. It behaves like it is, the touch is the same. The difference is in the processing. There are some additives inside that make these films cross-linkable, and the process, the so-called process we're talking about, is the cross-linking process, and this changes the material properties. An example for this is the so-called EVA film made of ethylene vinyl acetate copolymer. And of course, there are some combinations possible with other interlayers for making stiffer, for changing properties, and so on, depending on the requirements. The cross-linking, what does this mean, or the difference between thermoplastic and duroplastic-elastomeric films? What you can see here is an entangled polymer chain, right? At different temperatures. So you see a thermoplastic polymer behaves at different temperature, more or less the same. It can widen a little bit, but the structure of the polymer chain remains more or less the same all the time, depending on, or independent what temperature you have. You can always go from one to another material. It's in this temperature range we are talking about. It's all the time the same. Compared to this, give me a second. Okay. Here we are. It was too fast. Okay. In duroplastic-elastomeric, as I said, there are some additives inside, making the so-called cross-linking process and making a different thing. We need a certain temperature. It's normally, of course, the lamination temperature, as we have it in the glass industry, of more than 100 degrees C. And the additives are forming some connections between these polymer chains. These are chemical bonds, and they cannot be broken again. This means this process by heating up is irreversible, and we keep this structure of the interlayer in the glass laminate as it is. What this brings, I will show you in a second. Is nothing. The cross-linking step itself is nothing that comes from us. It's not invented by us. It is well known in nature. We are here in Finland. We have a lot of trees, a lot of wood around us, and it's well known for a long time that these trees can make a kind of a resin. And if you give enough time to this resin, it will be hardened. The product of it, well known for ladies maybe, it's amber. Right? Hard material, like a soft stone, let's say like this, made by nature out of this resin from the trees by cross-linking of the material inside. We don't have so much time, therefore, of course, we have this special kind of additives in the film, in the interlayer film, and you can see here a conversion of the cross-linking over time for different temperature. It is well known that this process is temperature-driven. The higher the temperature, the faster the process is going. And you see here typical temperatures that we have in lamination process, 130 to 150 degrees C. And this cross-linking step is changing the material properties. Here you see the properties of the film. If you take a cross-linkable EVA interlayer in your hand, you can stretch it up to 10 times, means elongation rate of up to 1000% is possible. You need a certain strength, but okay, not so much. If you cross-link it, the material properties will change, the mechanical properties. You need much more force to stress it, and you cannot get to this elongation as it was before. Means we give, by cross-linking, we give much higher strength to the film. Of course, we reduce the elongation rate, but it's still at a level of more than 500%, which is more or less okay for the applications as we want to see. Okay, now I'm bringing a few case studies with me because I want to show what's the difference between thermoplastic interlayer and the cross-linkable material. At first, we have chosen a bake test. It was already this morning in this discussion here. Typically, you run this test for 2 hours at 100 degrees C. Okay, normal behavior, no interlayer will get a problem. But then you have customers asking, okay, what if I need an interlayer or laminated safety glass with a temperature stability up to 200 degrees C? So the question comes, and we have done then a test in cooperation with an institute, making laminates, putting them into an oven, increasing temperature, and let's see what happens. As we have seen already in the former presentation, this is well known that PVB has a problem at higher temperature. when you achieve temperatures above 150 degrees C for a certain time, then you will find effects like this. You see kind of bubbles in this laminated safety glass. Thermoplastic ionomer, like Sentry glass, well, it's better, but you see on the edges that the formation of bubbles also starts at temperature of around about 180 degrees C. Compared to this, we have done this test with an EVA cross-linked interlayer, and up to 240 degrees C, when this test was over, we have not seen any failure on this. And you can see also from the edges, no yellowing or something like this. The reason for this finding is, of course, as I said, thermoplastic materials will flow at a temperature above the melting temperature. This means, or this can be increased or also influenced by humidity and moisture uptake of these films, and this will form like bubbles, as you can see here. This leads to loss of the adhesion to the glass, and finally to risk of delamination and, of course, loss of functionality. As I said, application for such application can be found in houseware. If you look on your bake oven, then it can be that some customers will do it of laminated glass, or even if we talk about fire protection, if you don't want to use fire protective glazing, but temperature with high temperature resistance of films with or glasses with high temperature resistance. Okay, second thing, mechanical properties. Next case study, safety glass under load. In this case, a customer in England was asking for freestanding barrier glass, freestanding barrier test, British standard. What will be done? Okay, you put a glass in a mounted system, and then you have then you apply force. In this case, as you can see here, 0.74 kilonewton per meter, and then you measure the deflection. The limit, you can see, you apply the load, and the glass will deflect in this direction, and you can see here the sensors for measuring the deflection. Once you have applied the pressure or the load, then you're waiting for 5 minutes to check what's going on, if there is a change in deflection, and then you increase it to safety level of 1.5. The test here was a comparison between EVA cross-linked and PVB, and you see the difference. The dark line is PVB. Of course, the deflection of this, I think it was 88 millimeter glass, toughened glass, and 0.76 or interlayer. There is certain deflection. The difference is not only the deflection value. The difference is that you have a so-called creep effect for PVB. And this is because the thermoplastic chains are moving between the glasses. It means there's a certain moving effect, and this is what the cross-linkable film will not do once cross-linked. You see this for the first step of load, and also for the second test when the test was done at a higher load level. Okay, also here we see applications for this, of course, well known in the market. Balustrades, we have it all around you. If you were at the yesterday evening in the lounge, you have seen a lot of balustrades around us, made of safety glass. Today there is a trend of making balconies on your nearby your swimming pool, maybe. In America, yes, hurricane glazing, we have it. And this can be improved further by combination of interlayers. On the left side, you see a picture when the after breakage behavior is important. This is an extra topic, not for today. Okay, and finally, I would like to say a few words about thin laminated glasses. We have done also some work here in cooperation with Technische University of Dresden, Institute Bauko. As you can see here, it was the aim of this project to transfer knowledge from normal safety glass to thin laminates. It was our approach to work with glasses with thicknesses of less than 2 millimeters, maximum 2 millimeters. We also were working with real very thin glasses here. Applications for this, of course, will be lightweight reduction, automotive ballistic, as we have heard already this in different topics, speech today's. Here, in this case, we have done a combination of different interlayers with the thin glass to see what effects can be achieved. The results of this, or some results of this project, are shown here. We have selected the ball drop test following EN 14449 in this test. And we have done constructions with different kind of interlayers with thin glass. In this case, I'm showing only 2 millimeter glasses. And we have chosen a certain height in ball drop test and have checked what is possible compared to normal standard safety glass, as you can see on the left side. And so we found out that by combination of the right interlayer, we are able to make such thin glass structures, achieving the same ball drop height as in this case, 30 millimeter thick safety glass. And this leads to a nominal weight reduction of more than 60%. As we heard already from Christoph, we are working all on the same. We can reduce, of course, the weight. We make lighter structure, hopefully better carbon footprint, and this is possible by combination of polymeric material, yes, of course, with thinner glass. Ladies and gentlemen, at this point, at the end of my talk, I would like to summarize a little bit before you can enter this door. We were talking about cross-linkable interlayers in glass lamination. They can offer different applications because they have slightly different behavior than the normal films, as you know. I have shown that the cross-linking step will change the material properties and the key properties of the laminated glass. As an example, I have shown you higher temperature stability for cross-linked materials, less creep. This means more resistant glass to load. And I have shown some results from thin or lightweight materials for thickness reduction by combination of cross-linkable interlayers and high-strength films. If you like, we are here. We are having a booth in this building. You can come along and talk. Maybe some of you have already seen this demonstrator as an example of lightweight structures. I'm here. We are here. Let's talk. Thank you very much for your kind attendance, and I'm here for your questions.